Hey, we're gonna talk about a little bit a slight deviation, but it's very relevant to MEV supply chain. Gonna introduce a programmable MPC for EVM world, because it's more relevant to intents and credible commitments. Um, I'm gonna start, and then my colleague Peter will basically give you more information. So here, in the next few minutes, I'm gonna talk about multi-party computation with a specific smart contract suite that we built called CIP, that stands for Common Interest Protocol. So that's the contract suite that has been using to control and manage the multi-party computation happens on off-chain. The idea here is scaling EVM capabilities with the cryptographic primitives. The reason is like you still have EOA as a first-class citizen, as a wallet, even though you have a smart wallet or contract wallet, anything, you still have to sign something with an EOA, right? So if we can abstract that away, then we can have account abstractions and all this kind of trustless coordination is possible, right? So this is the only implementation as available as a deployable MPC. Right, so what is MPC? Since it's not a cryptographic crowd, it's been touted as the crown jewel of the modern cryptography. It's from 1980s, it's been used for auctions, and 2005 onwards, the blockchain, advent of blockchain, we see this in various form of wallets and things like that. But that's not the thing that we've been using for nuclear deterrent and any kind of trustless coordinations can be solved. So all kind of usage has been touted. So in our case, in this construction, the MPC, the multi-party computation, is managed by a group of people, and that has been done with the DKG. So the DKG is the one the key shares, and that performs the MPC. So it's not a vanilla DKG service. That's to be very clear. This DKG has been used to run an MPC service, and it's controlled by smart contracts, and you can program just like any other smart contract. Anyone who's programming doesn't really have to know anything about cryptography. Just implement it, and the available service from the multi-party computation will do it. And the contracts, smart contracts, the CIP modules will be deployed by blockchain. So currently it only takes users who have a chain address. It's so user is interacting with the system will have some sort of a chain address, right? Cool. So currently it supports 6 chains, 3 chains is already deployed. Peter will go into that details. The key distinction between MPC that you see 5 blocks or Credo, you name it, all this kind of big boys, or any other wallets, it's all hosted somewhere. It's an off-chain hosted solution, and then you might be using that solution to sign a service for your service. But there's a very different dimension here. Is this is completely controlled by the smart contracts. Just think it like Gnosis wallet that you're putting at like multisig. We don't have a native multisig capability on Ethereum. That's why Gnosis wallet is there. And it's a rolling DKG base. What that means is once you have a committee, few solvers just don't want to do anymore, you can roll it. So it just editable, or rolling committees, it just keep going all the time. And solvers can come and go. It could be ad hoc. And one of the important thing here is like it's about more user experience. It works on any device. Any mobile, any browsers, you can have in-browser embedded signer service, anything like that, right? So out of the gate, you say it's a decryption service like threshold service or programmable signing in EIP 1721. Now you can have like contracts negotiate with each other, and then it will just be signed by one of the designated CIP. Privacy modes of the intents or the MEV operations can be possible. And this is a very important fact that you can have a trustless coordination between adversaries, passkeys or any kind of AA bundlers. And one of the key things that we are very much proud that we presented it, statement voting, private voting is possible. So you don't really have to dox yourself what you voted for, so you can just freely walk after that one, right? Currently, just very plug and play. We have toolings available, contracts are deployable. It is in the mainnet for the last year and a half, just doing one service as an MVP. There's a Ethereum validator signing key recovery. So that's been there and it's still serving. So that's the one of the fundamental in operations in Ethereum. It's been serving that, but more use cases are gonna come in, right? So the three parts that we have in this whole thing is a DKG, as I said, how the shares are splitted, and the computation service that we offer that's would be run by Solver, and then the how the whole thing is being managed by be controlled by a smart contract. So buckle up, let's go. Peter, spill the details.
All right, thanks, Matt. Hello everyone. So here you basically can see what's initial aim of MPC is. So basically you have like several parties who even do not know each other. They do not need to trust each other, and they are basically doing some computations. But the main difference here is that there are two basic properties that we have. So the first one is basically that these parties have private inputs, right? So any of these guys do not know any other guys' inputs. And we also have the other properties, which is the correctness output, which means that within the given x1 to x5, we get like deterministic result, right? Okay. Yeah, so let's talk briefly about the DKG, the distributed key generation, and how we use it in our protocols. So in our case, it's a 5-round robust protocol. Robust means that since even if it will stop, it could continue from the same step. You don't need to rerun this from scratch. So if something happens, you do not need to rerun. And what actually could go wrong within the DKG? It occurs that some of these MPC solvers, actually these participants are called solvers, MPC solvers, they can do some malicious actions, and since they do not trust each other, you never know, you only have to check, and if you verify the proofs, then and you see that these participants behave dishonestly, you could just post the proof and these participants would be invalidated, right? So the main point, the main purpose of this procedure is to generate some sort of common credentials. So the common credentials is something we are calling the DKG public key, which can be used for further encryptions of some data. But the thing is that these solvers would do some computations over this data, and for that they need their own distributed credentials. In general, we have this. We have kind of off-chain and on-chain logic. So on-chain logic is controlled like a specific smart contract suite, and these guardians, these solvers, are actually communicating within each other during this procedure. They are posting some data on-chain and then producing some computations over that. So they are identified with specific EC, DSA address and some ID of the registry. These registries are incompatible in terms of if you have like some amount of members, some amount of these keys, they are not interchangeable within the other committees, but I will talk about that a little bit later. The main purpose of the DKG is again to get some sorts of common credentials and some private credentials, which we call like shared credentials. Let's think that what actually could happen if some of these MPC solvers are not happy within the protocol. So since the protocol is fully permissionless, these MPC solvers could join or just exit at any time they want by any reason. So we kind of don't care about that. So how could we guarantee that the protocol would still perform like seamlessly, so the users would not even feel any changes when the committee is switching? So actually, what we're using is so this is something that is called a handover. It's another protocol. You can treat it as a tree of management. So imagine you had some set of solvers, and then you just then you just replace the solvers with another set. It can be so part of them could be the previous solvers. So it actually doesn't matter. But the thing, the key thing here is that the DKG public key that was obtained during the initial DKG procedure is kept the same. So the only thing that is changed is just the shared credentials of the new committee members. So you could continue the operations of your system. You could perform some requests. It doesn't matter. You could just keep going. And you don't need to rerun the DKG procedure. You don't need to get the new DKG public key, so whatever. Regarding the general MPC flow, so we talked about already the DKG and the handover, right? But we also need to cover the MPC, so how we are working with it. So let's consider the example that so the DKG is finished, and we have this DKG public key. And the user could encrypt some data. So, for instance, in our Stakehouse protocol, it is a BLS signing key, but in general, it can be whatever data you want. And then let's imagine that you have also a requester who submits the key recovery. Actually, the eligibility of this requester submission is like fully depends on business logic of application that you run off top of this protocol. So it could be anything, but the next step is that this requester submits this key recovery, and these MPC solvers are performing some computations over this data. They are just processing these requests, and so they are doing these computations and pushing this data back on chain. You may ask, like, why do we need that all for? So for what we are doing that? So the answer is that we would like to recover this data at some point in the future. So remember this requester who basically sends this request after these MPC solvers submitted some data on chain. He could grab them. He could decrypt them and assemble and get like the very starting value that was encrypted previously on the first step. I already said that requesters should comply with some additional business logic on top of CIP, but that depends on the application you are running on top of that. One more important thing, that no solver can actually get the value of this requester key. So they're doing some computations over that, but they never reveal this value to someone else. So the requester is the only person who will be able to recover this, right? Here we have some slides. I won't come into these nitty-gritty details. So this is just a table with a bunch of cryptographic algorithms that we are utilizing here. So there is a DKG among them, and we are just listing the purposes, like for which algorithm we are using here. Also, this table is about our deployment for the Stakehouse, which is, as Matt stated, is operating for about a year or so. So here we're also utilizing various, let's say, actions within our entities, like SafeBox contract suite, like Stakehouse itself, and MPC network. This is something I wanted to demonstrate to you. So this is the recent deployments on Gnosis chain. So as Matt said, it's fully EVM compatible. You can deploy it on any chain you want. So here we just have a plain text, and we are encrypting it on DKG public key and send some transactions within this QR code. You could check these encryptions and also the decryption requests. And after that, these guardians, they are fully independently run like the network, and they are processing these decryption requests, and they are performing some computations on top of that. After they performed some computations, so the requester could grab this data, decrypt them, and basically assemble them and get the initial plain text. So one thing I wanted to note here, that all of these protocols, so all of the three protocols that we covered, like DKG, like threshold decryption, and handover, are threshold protocols, which means that so it's kind of T out of n participants. So n is the number of of all participants in the network, and T is just the threshold, which actually the maximum amount of dishonest participants the system could tolerate. So we have some specific security notation here, but it's common in most threshold protocols. Yes, so we have several important properties, but to name a few, we utilizing a security first approach, which means that the more MPC solvers you have in your network, the bigger the threshold value. So the bigger the maximum amount the system could tolerate, and thus your security becomes stronger. You could deploy it on almost any EVM compatible chain, and you could use it for any democratic governance problem. Yeah. So now I'm making handover to Matt.
I don't have the threshold, but I will take the handover. But so I want to take a step back. Why this is important, right? All the DKG MPC deployable. Here we show this is a Gnosis. It's a MPC, but what you can do is, like, it's even though the CIP is a Gnosis, if you want to do some actions on Ethereum, you can call this guy, and you can do it in computer cheaply, and you don't really have to wait for anything. But remember, this can be done with a smart contract call, because it's completely smart contract operated. So that then the picture here is in 2017. You get this kind of multi-sig capability as a safe, but it's not just a wallet. But it is a wallet, but it's not just a wallet. We see that what it could do when the DeFi took off and the DAO took off. It's like more of like, how many people can do all the programmability on the top. Similarly, in 2023, now we are injecting MPC capability on a smart contracts driven, which that means the complete programmability will be available, and people don't really have to worry about anything underlying the cryptography. But you can, as a cryptographic primitives that people who care about, they can add additional module to the cryptographic. So the SDK will definitely help the implementation of the contract templates and things like that. We are doing this tooling currently since it's a deployable. Anything that you can deploy for your friends. That's it. Or you want to deploy it for DAO, just like a multi-sig. Or you can have a network level ad hoc deployment, like we said for the stakehouse. It's used the Ethereum validator. What it does is like it brings a verifiable proof for the trustless coordination. Let's say if you want to do some sort of a credible commitment devices, this is available for you anytime, right? In a more practical sense, what you can do today with this is like, you can build any kind of provable mechanism on a smart contracts, and you can do that in off-chain, or you can create like in a private intents, as I said, like, combining with our intent computer before. If you have some 1,000 USDC here in Ethereum and you want to do give to Bob on Optimism, you can sign it on Gnosis. Because it's pointed to the public key, the DKG public key, and all it matters is like it's a decryption, it's the data, and and you are the one decrypting. The MPC network never touches the data. Remember this. It produces a computation. It's give you zero knowledge proofs, and the script. The script could be like in any phone or anywhere that you can do it. You click a button and it will just prove yourself you're the one, and you give a recipient on other side. The intent is now going through a different kind of a transportation layer, right? Cryptographic transportation, and now he gets the money there. I mean, if there's a solver, then that's what. But maybe without a solver, you can do this way too. So we are giving this all kind of probabilities, how the multi-chain composabilities can work when absolute liveness is not possible. So intents are kind of the major assumption is we are giving up the liveness of the chain. When the market tanks, we'll see how it works. Maintenance will come up, Kraken and Coinbase does. Hopefully not. We'll see. The auctions are another one thing that we are pretty much very excited to see that, very few members of people who coordinate, but they can escalate the price, flip the game, you pay to win, and then the game will flip, then you start paying not to lose and stay in the game, right? Because the other party will just escalate. They know that you're going to pay, and then you need to get its inclusion. So all these things, the no auctions and things like that can be possible, or outside of our context, but you do the private ML for some sort of an ML agents. So it's all kind of things are possible. I'm just stopping here because MPC is a wide topic. I don't want to take all the time. Let's talk about intents more. Thank you. Any questions? Okay, go ahead.
So you had that slide that said, smart contract wallets are the past. This is the future.
No, that's not. I said smart contract wallet came in 2017. Now the decommon comes in. It actually works with Gnosis Safe. So it basically, even if you have a Gnosis wallet, you need an EOA to sign, right?
Yes.
Right. That could be there. So it's like complementing. Yeah. That's a shift in Ethereum.
So you still see permissioning happen at the smart contract level?
What is the permissioning happening at smart contract?
Yeah, let's say you want to issue like a session key to some counterparty to be able to interact over a subset of your wallet and the access that it has.
We borrow all kind of problems Ethereum have. Yes. But you do have some sort of a cryptographic things. Only thing decommon brings is MPC computation can be managed with the smart contracts. Any vulnerability in the smart contracts, it is there in this case. Yeah. Ephemeral keys. Oh, ephemeral keys. That's what you asked.
Yes,
about.
yes.
Okay. Yeah, you can do that. Yeah.
But the permissions for those ephemeral keys will still happen at the smart contract layer, not at the MPC layer.
No, you can do at an MPC level. This is one of the things that we're talking like, how can you create a session keys? So rather than giving that power to smart contracts, you assign this. But then it comes down to which CIP that you want to point to, right? Generating that ephemeral keys.
So, and those ephemeral keys can still constrain the state access the same way that
you can time out. Low. So it's just like only for like in a few seconds or something. Or
but can you constrain the state access, or is
it? And yeah.
You can.
Yeah.
Okay.
But you have to do that just to make sure that what kind of authorities that you're giving to that session keys, right? So it's on you. When you deal with smart.
No, I understand the safety assumptions.
Yeah.
I wonder what is a constraint on the permissioning system.
Depends on you what you are using for. But session key can be created, ephemeral keys can be created, and can be constrained to a certain state. Similarly, that what we do is like an instance computer that we constrain everything to an accumulator map, right, to a state. So yes. Rather than putting a contract everyone, your tokens are mapped to an accumulator hash in a sparse Merkle tree. So similarly, you can map this from a key to a particular key, and that can be constrained. Many ways you can do it. Thank you.
Thank you.
Have you heard about the MPC wallets by Lit Protocol that they are doing, and also the PKP basically? So they have a really evolved version, something called the Lit Actions, and their programmable PKPs have like this JavaScript functions that can run on chain or off chain, basically.
True. So all the MPC wallets, there's about 20 of them, but there are different iterations. So that's what I said in the beginning. You have MPC wallets, but there is a problem with that. Not a problem, actually. The status quo is the MPC itself is not controlled by the smart contracts, right? That's the biggest paradigm change here. The MPC computation is controlled by the smart contracts. Now you can have MPC wallets. You can use MPC wallets can also use this. We're not doing an MPC wallet. Could be done, but we're not interested in that one. This is more about how can you bring MPC capability at the smart contract level, right? Okay, so now you can control the off-chain computation. All right, thank you.